Okay, we're just getting started on CR. So CR is computed radiography, and we're going to go over just the basics of that. So CR systems are cassette-based. They're cassettes that have a phosphor screen. When the X-rays hit that phosphor, they form a latent image. The cassette is placed in a reader or a CR processor. A red ruby laser is used on it to release those stored photons. It collects the signal and digitizes it to be displayed on the screen or the monitor, which you guys see the image on. Okay. If you see PSP, it means Photostimulable Phosphor. A PSP plate, that means CR plate. So if you have a test question or on your boards, that means they're talking about CR. Okay. So it's cassette based. It has a durable, lightweight plastic material that's backed with a thin sheet of aluminum that absorbs X-rays. The PSP, or the photostimulable phosphor, is the chemical coating on that plate. Instead of an intensifying screen, which we're using film, they're using that. They also have a barcode label on them. Most of the machines or the CR readers have a scanner. If it's old like ours in our lab, it doesn't. But there's a barcode on it that you can scan. All right, here's the basics of how it's constructed. It has certain layers. So there's a protective layer, which is the thin, tough, clear plastic that's going to protect the active or phosphor layer. It's made of carbon fiber or magnesium. It has no image producing capabilities. It's there to protect, hence the name, protective layer. The phosphor or active layer. This is the layer of photostimulable phosphor. That phosphor comes from the barium fluorohalide family. This really is probably the most important layer here, or one of the ones that you're probably going to get asked about the most. It has the ability to store and release energy. So this is where our X-rays are going to be stored. The conductive layer is a layer of material that'll ground the imaging plate from electrostatic charge. It increases spatial resolution by absorbing light. The support layer is a semi-rigid material. It gives the imaging sheet some strength. And then we have the reflective layer, or the light shield layer, that sends light in a forward direction when released by the reader. And we want to prevent unwanted light from affecting the unexposed latent image. And then the backing layer is a soft polymer that protects the back of the cassette. We don't want any unwanted background radiation to kind of affect the unexposed latent image. So something I want you to do, though, is write out these plates. I want you to know them in order. If given a list, could you drag and drop them into an order in a row? Remember, protective is like the bodyguard. That's got to go first. The backing layer is going to go in the back. Okay, so why don't you practice with that? Reading sequence. You make the exposure on your CR cassette. You bring that CR cassette over to the reader. Scan it if you have a scanner for your barcode. You're going to put the plate in. The CR reader is going to take it in and process the image. So the latent image or invisible image is just going to be sitting kind of in that phosphor active layer until it's released. So a red laser light is used. I call it the red ruby laser. The CR reader uses this red laser to scan the information. When the red laser hits that imaging plate, or that phosphor, the plate releases a blue or violet light. Depending on what book you use, it'll be blue or violet. The light is then captured to create the manifest image, and the manifest image is the visible image. Okay. Then that imaging plate, while still inside the reader, is hit with a bright white light, and then that erases any information that was on that imaging plate, and that imaging plate gets clicked right back into the housing of it. So this is a little picture of inside that CR processor. So there's these different rollers. So when the imaging plate gets clicked in, it actually opens the locks and the plate is taken out of it, out of the housing. It goes through these rollers, then it's hit with the red light, emits the blue light. The red laser scans in a specific pattern. It's called a raster pattern. So down here in the corner, you can see the pattern goes left. The arrows here, we're going to follow the arrows, and go kind of left to right, up and down the imaging plate. So the pattern of the red laser is a raster pattern. I always kind of see that in there, so that's a term I want you to remember. The laser scans multiple times as the imaging plate moves through the reader, and this is called translation. The light is produced and then detected by something called the photomultiplier. All right, when the red laser hits that plate, it releases the blue light. Laser is an abbreviation for light amplification by stimulated emission of radiation. Do I think you really need to memorize that? No, probably not. But something I want you to remember, because sometimes I see slow scan, fast scan questions. The mechanism that moves the imaging plate, it moves it constantly but slowly. That's called slow scan. The fast scan direction is the movement of the laser across the imaging plate. So the fast scan deals with the laser, and the slow scan deals with the pushing of the imaging plate through there, okay? So raster pattern for red ruby laser. Then we hit the photomultiplier and the ADC. The photomultiplier tube is used to convert small amounts of light into amplified electric signal. Then what do we do with the electric signal? Well, we send it to the analog to digital converter, or the ADC. It determines the numbers of shades of gray in the image. So it specifically takes those electrical signals and converts it to a picture that we can see. And, you know, majority of our exams is black, white, or a version of gray. And it'll decide within the pixels in our matrix, which we'll get into later, which of those falls, or the shade of that color for that specific area will get placed in our image. Another term that we're going to get into detail later on, but I want you to know sort of definition at minimum at this point, is the histogram. So when you choose your setting on your control panel and you're going to process your image in the CR reader, the control panel selection, say of PHS or lateral hand, each of those options has something called a histogram, and it's a graph. It's a graphical representation of the numerical tone, which is your grays, black, white colors, of an X-ray picture. So each setting, PHS for this one, has a graph of where it thinks the levels will be, which is why it's important to process your images under the correct settings. So AP chest histogram, there's a specific number of where it expects low attenuation, high attenuation, so things like lungs will be black in color, right? Bone, mediastinum, right here, vertebrae, sternum, they're going to be white. Anatomy selection is important. So choosing the correct setting, I think, is really important. You want to make sure you're processing the image under the setting that's selected, because in the background they all have their own settings, right? So there's something called raw data, and that is the data that's collected before the processing computer applications kind of make it pretty. They correct any issues that it can correct for at this time. So the example over here is an AP knee process as a knee, and then a knee process as a skull. And for your selections, when it processes, it's going to give you a resulting number. If you don't process it under the correct one, your number is not really going to be accurate. And the lookup table, because we've moved to digital imaging, the lookup table is something that also happens in the background, near kind of when your histogram happens. So this isn't something you control as a technologist. It happens in the background. It takes the raw image and adjusts the pixel values according to the part that's selected. The lookup table is the primary controller of digital contrast. Okay, it's a mathematical formula that's producing the correct amount of brightness and contrast. It's not a calculation you're going to do, nor something that you're going to change. But digital contrast is controlled by the lookup table. Remember that one. Exposure number, or EI number, for CR, we use an S number, and S stands for sensitivity number. The purpose of an EI number is to let radiographers sort of have a gauge of their technical factors and resulting in overexposure or underexposure. Okay. With CR, the annoying part is that the S number is an inverse relationship. What does that mean? An high S number means you used not enough technique, or it's underexposed, and a low S number actually means you overexposed or used too much. All right. So I know that's a little bit confusing, but your underexposed images are actually going to have a high number. They're going to look mottled, grainy, noisy, and your low number is overexposed, and it's going to be a little bit saturating. So the S number isn't just technical factors. So if you're not perfectly centered and collimated, it's going to take other things into account. It's going to decide if you had your field of view too big. Do you have too much scatter? Was your distance wrong? Did you have collimation? No collimation? Did you run it under the correct histogram? Was there a delay in processing time? Did it get left somewhere for a few hours? I don't know how that would happen, but just as an example. So it's not only technique, it also depends on if there's hardware in there, if you correctly centered, things like that. So it's not just technical factors, but kind of the main. Erasing of the CR cassette, ideally, is after the exposure is processed, and it does it right in the machine, if possible. The imaging plate will hold your picture in that phosphor layer for up to 8 hours before it starts to disintegrate. If you need to erase the cassettes, they recommend secondary erasing the CR cassettes every 24 to 48 hours. And then that means secondary radiation or scatter, or just being out in a hallway, in a storage room, something like that, not being used all the time. Erase those. And then primary erasing you would use anytime, say the cassette got left in an X-ray room. If it was near the primary beam, you'd need to primary erase.